Okay, we've got quite the problem here. You may have noticed it while flipping through that we've got this paragraph, and then on the next page we've got an A through I to fill out. So we're just going to walk you through a situation like this. And
I'm recovering. I'll be there in just a second.
Yeah. So example 9, Bugsy and Mugsy, an unexpected journey. So while working on the computer, Chris observes a bug walking on the screen of the monitor and traveling in a straight line until it leaves the screen. Chris knows that the rectangular screen is made up of little square units called pixels, and his screen is 800 pixels wide by 600 pixels tall. So here we have a graph that represents that 800 by 600. Notice that the scale is not the same each direction. On the bottom, every line represents 50. Going up, every line represents 25. So that is going to be important here in a second. Suppose that Bugsy enters the left side of the screen 100 pixels up from the bottom left corner, and that at the end of each second, Bugsy has moved right 2 pixels and up 3 pixels from his position at the end of the previous second. Well, skipping ahead at the end of this, we're going to have to sketch the path of... Oh, wait, no, not skipping ahead. Right there.
Don't skip ahead.
Sketch the path of Bugsy. So he starts at 100, which is right here, and then at the end of a second, he will have gone up 3 and right 2.
Now, up 3, right 2.
Now, because of my scaling here, I'm going to go up 3 50s. Okay, so I'm going to go up here. This is 1, 2, 3. I'm going to go up by 50s, and then if I go right by 50s, that's just 2 lines. So that gives me a place right there.
Right.
And then I'm going to use my straight line tool that I have. You should just go ahead and maybe plot some more points, and then
you want to get as many accurate points as possible. And also, just a little word of caution here, the reason that we're counting by 50s is because the scaling on both the x and y axis are not identical. So when you're going for that slope, you want to have...
You want them to be identical.
You want them to be identical.
And so, but we've already got this graph here to use, so we've got to make it work.
That's okay. And we can make it work because we're geniuses.
Right.
So.
And it does say to clearly indicate the starting position. He starts over here at 100, and he's going to the up and right. Now let's talk about Mugsy.
Mugsy.
Simultaneously with Bugsy, a second bug, Mugsy, enters the right side of the screen, 150 pixels up from the bottom right corner, which would be right here.
Right, at 150.
Uh-huh.
Yep.
And then at the end of each second, she's moved left 4 and up 1. So if we
count in 50s.
So this is 1, 2, 3, 4 50s, but when we go up, we actually need to go up twice. Because we're going up a 50, which is 2 lines.
So that our slopes are correct.
Right, and if I keep going with this...
3, 4, and then up 2 50s.
I'm going to run into the y-axis. And that might be helpful for us to be able to, you know...
Bam, right at 350.
Find the y-intercept at some point during this
Thank
problem.
goodness.
All right.
We got to that point on the y-axis.
All right, so
we started. Now, we'll clearly label where we started, though, Mrs. Stevenson, because it's right there. Yes, okay, there we go.
Okay, so it asked us to sketch the path of Mugsy and everything. We did that. Now we're going to work out some problems. So first, we want to fill in this table. And so at time 0, Bugsy is at his starting position. And his starting position is what?
0, 100.
Right. Okay, because that's over here.
Right.
Now, we drew our next point way up here, but after a second, how far will he have actually moved?
Well, he's only moved to the right 2 pixels and up 3. So if you go right from 0, 2 units, that's 2.
Right, and then if I go up 3 from 100.
Is 103.
And so what we can do is we can continue this down. Every second, he's going to keep going right 2. So this would be 4, 6, 8, 10.
Right.
And every second, he's going to go up 3. So that's 106, 109, 112, 115. And you could keep going. We just decided to have this much.
Yeah, like that's where we're good.
All right, so where's the starting position of Mugsy?
So, okay, Mugsy actually starts way over on the other side of the screen. So his actual x-coordinate is 800.
Right.
And he starts at a y-coordinate of 150. So that's his starter.
Right.
And then he moves 4 units left.
Every second.
So
we need to subtract 4.
Right, so he's not going to 800 4. That's not on the screen.
That's not the right way, no. So subtracting 4 each time gives us these values. And then for his y,
for the y's now he's going up 1 unit every second. So that's pretty easy. 151,
yeah, it's like
152, 150, whatever.
Note to self, Hazelwood can only count to 153.
Did I get to 153?
I don't know.
I think I stopped at 152.
Yeah.
So, yeah.
All right, so we're going to use this, and I'm sorry for the unfortunate page flip that you've got going on, but we're going to use this to fill in A through I on the next page of your notes. So here we go. First off, write 2 sets of parametric equations to model the information in the table for Bugsy and Mugsy.
Sounds easy enough. 1 for each color.
Okay, so we start off with Bugsy. So we could call it X1 or we call it XB.
Hey, XB.
For Bugsy. And so if we look at just the X values, that we've got 0, 1, 2, 3, 4, and 5 for T. We've got 0, 2, 4, 6, 8, 10 for X. We're basically trying to make an equation out of those 2 things.
I feel like we're doubling T.
We are. We're doubling T. Every time that we go a second, we have twice that much for X. So we would have 2t. We could also think of this like a slope-intercept kind of thing. That we're starting at 0, so it's like a plus 0, and then we're adding 2 each time.
That's good.
So
that's a good way
2t.
to think about it too. Okay.
And so that's helpful for YB, because for Y we've got same T column, 0 through 5, and then the Y column starts at 100 and goes up 3 every time.
So we got to be 100 plus.
Right. So 100 plus.
And then 3 every time we move.
And so every time that I add a second, I should be adding 3.
Right. So there's the, which one is that one? Bugsy.
Bugsy.
There's the Bugsy parametric equation right there.
Now let's do Mugsy.
Let's do Mugsy.
So now
Mugsy.
We are looking at. I'm gonna sneeze.
Say cheetah.
Okay.
Did you say cheetah?
I didn't. No, it went away. So now we're looking at the 0 through 5t column and the x column for Mugsy. So we've got that starting point is 0, 800.
Yeah. So now this is going to be 800, but we're going to move left, which is a minus.
Right.
sign.
So every time we're subtracting 4, so that's going to be minus 4t.
Yeah, I like
and
it.
Then y Mugsy is we're starting this time with 150.
Right, but we're adding still, because we're going up the screen.
Right, we're adding 1t every single time.
Right.
And hopefully this makes sense, because you may be inclined somewhere in here to have like 3 halves or -1/4. Those are the slopes of those lines, and we'll use that later.
It's coming.
As far as the parametric equation goes, like we split those up into their x parts and their y parts.
Right, and that's what a parametric is. It does all the splitting of the stuff.
Absolutely. B, give the location of Bugsy in ordered pair after 20 seconds, 25 seconds, and after 50 seconds. Well, we just have to plug in, right?
Yeah, that's the t value there. So in order to get the actual ordered pair, what they're saying is t has to be 20. And so everywhere you see t for the Bugsy equations, you just put a 20 in there.
Right.
And by the way, you will never get a point of just an x value, of just a 40, or you'll never get a point of just a y value, which in this case would be 160. You always get a point with x and y.
Which is why it's kind of giving us a hint that our answer should be an ordered pair there.
Right.
So after 20 seconds, Bugsy should be at the point on our graph 40, 160. And then we're just going to continue plugging in. So for 25 seconds, we just need to do 2 times 25, which is 50. And then 100 plus 3 times 25.
175.
Right.
And remember, this is an ordered pair. This is not just an x and not just a y. They go together to tell us exactly where we're located on the xy coordinate system.
Absolutely.
That's right,
absolutely. And then
50.
2 times 50 is...
Hundy. It's a hundy.
100, like the car?
Yeah. I wasn't thinking of the car necessarily, but hundy.
250.
Like 100, it's a hundy.
I think you're the only person I've ever heard say that.
Gosh, you never watch Wipeout.
Oh, I've watched it a couple times, maybe. After how many seconds will Bugsy leave the screen? So let's think about what that's asking us. Bugsy leaves the screen.
At the top of the screen.
At the top of it. Let's go back and look at our graph.
See, that's the green line.
Up here. Right up here is what we're looking for. We're looking at where is he leaving Is it where or when?
Where I believe it's where.
After how
After how many
seconds?
Yeah, so we have to
Bugsy
figure
leave the
out
screen?
when the y coordinate then is equal to that, because the next step he takes, he's off the screen.
Right. So we want our y for the parametric equation to equal 600.
Right.
Okay.
600.
Yes.
Okay.
Exactly. So 600 equals, and we're going to set it equal to our y equation, 100
for
plus
Bugsy.
3t. So to solve, I'd subtract 100. You get 500 equals 3t.
Well, and in a real world situation, maybe in a real math world situation, we would do 500 by 3 and be like, oh, that's the answer. But if you were to ask me, Mrs. Stevenson, how long is 500 thirds seconds?
I wouldn't know.
I wouldn't either. So in this case, let's go ahead and just figure out a decimal that we can actually use. 500 divided by trace. What? My calculator said
Control enter.
Control enter. It's 166.6 seconds. So this bug's really taking its time crawling across the screen.
I don't know. That might be pretty fast. It depends on what
It's
kind
like
of
3
bug,
minutes.
right? Well, okay, yeah, sure. Okay, so after how many seconds will he leave the screen? After 166 seconds.
Right.
At what location does he leave the screen? Well, we know that he's leaving it at a y value of 600
Right.
because we looked at our graph and we said, well, he gets to the top.
Going off.
So we need to figure out now what the x value for that coordinate is, and we can figure that out if we use what we just did,
Right.
that 166.6 seconds or 500 over 3.
I think the 500 over 3 will actually give us a more accurate answer because we don't have any rounding issues with that.
That's true. So if we go back to our x equation and we plug in our time
of 500 over 3.
Then we get 1,000 over 3,
Ugh.
which is so much better than 500 over 3
I know
was.
exactly what to do.
Okay. Control enter. Bam.
333.3 for the x coordinate.
Which I didn't really leave myself enough room in that. That was unexpected.
Unexpected indeed. But anyway, that's the coordinate position at which time this guy is off the screen.
Let's go back and look at the graph real quick and see if that's right.
Let's see if that makes sense.
333. Yeah.
You know what? It looks pretty good.
That's exciting that that's right.
That's
Okay. Let's go.
Next one. Right there.
All right.
Okay.
Part E. Give the position now of Mugsy after 20 seconds.